Hello everyone, I hope you're doing well. In this video, we'll be talking about Dirac notation in quantum mechanics. So Dirac notation is a notation that is used to represent states, wave functions, and operations in quantum mechanics in a concise and convenient way. Okay, so let's write this definition down and then we'll understand it, the notation and everything about it. Okay, so it will be a quick overview because Dirac notation is just a notation. You should understand what each symbol means and that's it. There is nothing to worry about and there is nothing to dig deeper into. It's just a notation. Keep calm. Dirac notation is another way to express the state. You can say psi because we represent states by wave function in normal representations of system in quantum mechanics. It is used to describe or write quantum states and quantum operations in a concise and convenient way. Okay, it just compacts the lengthy writings into shorter versions. So it's just like you are writing a whole thing, and in Dirac notation you are writing in this way. Okay, it just makes it concise and compact, and it's convenient to write down. Following the rules, you can do the whole calculation so easily. It's really easy for quantum computation. It is used for convenience. There is nothing you can say anything else about it. I've used this notation to solve some of the perturbation problems, and I used this notation coupled with the knowledge of layer operators, and the experience was seamless, I must tell you. Otherwise the calculation would have been so lengthy and so complex that I couldn't do that. That's a lifesaver. So learn it and apply it and practice it many a times. So let's get back into the video. So let's see what representations we have in here. So normally we have wave function. We know that in quantum mechanics we encounter with wave functions which are represented by psi. In Dirac notation we represent wave function, or we can say states, by ket, and the ket is represented by, it starts with this straight line, and then you'll write the wave function here and it encloses like that. This is a ket vector, or you can say simply ket. Okay, it's like that. Okay, that is a ket vector. You can say ket, you can say state vector, and it's easy to say it as ket. Okay, that is a ket vector, and we know that in quantum mechanics it's also common that we have psi conjugate. So if we represent a simple wave function by ket, then how we can represent its conjugate in ket bra notation? We also call Dirac notation as ket bra notation. Okay, because it involves usage of kets and bras. So what is bra? Bra vector is used to represent the complex conjugate of a wave function or the complex conjugate of a ket. Okay, so if you want to represent a wave function, you'll use ket. If you want to represent the complex conjugate of it, then you'll use bra. So if psi is represented by ket, then psi steric, which is conjugate of it, complex conjugate of it. Complex conjugate means that, for example, if psi is equals to e to the power iota x, then psi star, which is complex conjugate of it, would be equals to e to the power minus iota x. Wherever it's iota, you'll replace it with negative iota. That is what the complex conjugate means in normal terms. Okay, when it's matrices, the situation becomes different. there is additional step that you have to do when it's expressed in terms of matrices. Okay, if the wave function is represented like that in a simple way, then that's the simple conjugate. Okay, that's the way to compute the conjugate. But if it's matrix, if the psi is represented in terms of matrix, then psi star will not only involve replacing iota by minus iota, but you have to take transpose of it. We'll see it later in properties and application, so don't worry. So I was talking about that psi is represented by ket, psi star would be represented by bra. So bra is like you start angle bracket first, psi and star. This means psi star. This is bra vector, this is bra vector, and this is the ket vector. Okay, so ket vector is simple, okay, while the bra vector is the conjugate of simple psi. Alright, so these are the two basic notations that we have. This is the bra vector and this is the ket vector. Next we have the scalar product. Scalar product is really common in quantum mechanics. We have seen these integrals multiple times. Let's say it's psi 1 steric, psi 2 dv. Okay, this is the scalar product of psi 1 with psi 2. So we have this situation. How we can write it in ket-bra notation? That's a really frequently occurring notation, integral in quantum mechanics. So let's write it in ket-bra notation. How we can write it? So we can do it. We can see it's psi 1 star, so it means it's a bra vector. It could be written as a bra vector, so we'll write the bra vector first. We always write the bra vector first in scalar product. Okay, so we'll write psi 1 first and like that, and then we have psi 2. Since it's a product, so we'll have this common line to represent it, and we'll write the ket, which is without the conjugate sign, in here. Okay, so this is the representation of scalar product in ket-bra notation or Dirac notation. So this means that it's a scalar product of psi 1 and psi 2, and there will be a complex conjugate on psi 1, and psi 2 will be simple. Alright, so other than that, we have another thing that happens is when we have operators involved. Okay, let's say there is a operator A with a hat over it. So if then how we can incorporate it inside this notation? So let me tell you that expression. There is another integral that is really common in expectation values, and it's like that. Let's say, okay, A applies on psi 2 dv. Okay, this is a kind of operator that is involved when we are finding out the expectation value with respect to this operator. Okay, so it could be the energy operator. Let's say this could be the energy that we are calculating, and we'll have Hamiltonian operator right over there. So I hope now you can recall this thing. So we can write it like that. We will have the bra vector first. Okay, psi 1. You are not supposed to write star over there because you already have written it in this form. Okay, so you have written it in bra vector, so it's totally understood that when psi 1 is written outside of this bra vector in the form of integral, you will put star over everything that comes out of it. Okay, and you will see if there is a constant involved in here. Let's say it's A. When you write it right here, there will be star over it. It means we'll take the complex conjugate of A as well. Okay, so you'll see this property later on. So we'll write like that, psi 1 in bra vector, then we'll write the operator because it's next in line, so we'll write the operator and then we'll write the ket vector. Okay, so there will be two lines in here. When there is a product of two wave functions, then there will be a single line in between. When there are three terms involved, then there will be two lines and so on. Okay, so that is the representation of this is a kind of operation. You can say A is being operated on psi 2, it will be solved and then it will reduce into a scalar product. Okay, so that is it. These are the actually main formulas. Let us write them in neat form so that we may know that what we have understood so far. So first of all, we have kets, which we represent by this sign. Then secondly, we have bras, which represents actually the complex conjugate of psi, and there is a property that every ket has a corresponding bra. Okay, in direct notation we have bra to every ket. Okay, because you can see it's understood that if you want to calculate bra vector, then if you know the ket vector, then we will take the complex conjugate of it and you'll get its bra vector. Okay, so that's simple. And thirdly, we saw the scalar product, that was psi1 then psi2. Okay, that's the bra vector and that's the ket vector part. And then we have, if we have operator involved, then we can write it like that. Okay, order matters, so everything that is written in bra vector, okay, it's complex conjugate of psi or psi1 or whatever it is. And okay, these are the actually basic rules. All right, and we'll be incorporating these notation later on in videos, and it will be really clear to you people. I'll be solving some of the examples where I'll be calculating the bra vectors to some of the kets in matrices in simple ways and all that, if you want to if you really want to understand it. Okay, so I'll do that in next video. And for now, let us see what if we had a multiplied by psi1, okay, and b multiplied by psi2. Okay, so it's just like if you are multiplying 9 by 3. Okay, this is one quantity and this is another quantity. So if it was 9a and 3b, so you can take a and b outside as well, so you can write ab 9 into 3 as well. Okay, so it's just like we can take a and b outside of this Scalar notation as well. All right, because they are just constants being multiplied. And if we take b outside of it, then it will come simply like that, because it's from ket vector. But if you are taking a constant outside of the bra vector, which is here, you can see a, so you will write a star, because by rule we know that the bra is in complex conjugate space, so everything that comes out of the bra vector will have a complex conjugate over it. So by rule you have to put a star over it, and if you know the value of a, you will find out its complex conjugate and write it away. Okay, so that is it. And there is another thing that we see, that if we have, for example, this situation that we have psi1 here and there are two terms here, let's say it's psi2 plus psi3, like that. Okay, you can imagine the brackets here. It's just like that this bra vector multiplies with psi2 and then plus sign and multiplies with psi3 as well. It's just like if you write 9 into a plus b, it's just like that. 9 will be multiplied by a and b as well. You can write 9a plus 9b. Simply what we can do here is to separate the bra vector with each of these gets. So psi1 will appear with psi2 first, this psi2 first, closes, then center is the plus sign, so we'll write plus sign, then bra vector again, and you write psi3 here and close it. Okay, so this has been changed into two scalar products. All right, the same applies when we have two wave functions in the bra vector. So let's do that. Let's say we have two vectors in bra space, so we have this situation. So the same thing will happen. This is psi3 that is being multiplied to psi2 and psi1 as well, so we'll write it with psi1 separately and then with psi2 separately, and we'll have plus in between. And if it's minus in between, then it will be minus. So psi3 with it, then minus sign, then we have psi2. Order matters, you'll write the bra vector first, psi2 and then psi3. Okay, same goes with their constants. So it's if A and B, so you write A and B with them, and you can take them outside. So it's A star and B star because they are coming from bra vectors. Okay, so I hope you got it. That is it that you should know. And if you want to write, for example, normalization condition in ket bra notation, so what happens in normalization condition is that we have the self product of wave function is equals to 1. The scalar product of wave function with itself is equals to 1. That is the normalization condition, and you write it like that. We have psi here and psi here again. That should be equals to 1. That is the normalization condition. And integral, in integral form, you write it like that, no? dv equals to 1. This happens when we have psi star and psi, which means we have psi in the bra and psi in the ket. So that is the ket bra notation for normalization condition. Okay, and if we have orthogonality condition, then what happens is we have two different psi and they should be equals to 0. That is the orthogonality condition. All right, and there is one more thing that I wanna mention. We also know the eigenvalue equation. We can also write eigenvalue equation in Dirac notation, and we know about Schrodinger's equation. In Schrodinger's equation, what happens is that H operator applies on psi gives the energy times the psi again, where E is the eigenvalue of Hamiltonian operator that is H here, and H, this ket is the eigenket for H. Okay, so if you want to add the word eigen to the value and the kets, then they must satisfy this situation. Okay, this is the eigenvalue equation. Here E is a constant quantity and it couldn't be a variable or something like that. And if the situation happens when the operator is applied on a ket, and after simplification you get the ket back times a constant quantity, then it means that that wave function is the eigenfunction of H, and the constant value that you have got as a multiple of the psi function is actually the eigenvalue corresponding to that operator. If this operator is energy operator, then the constant value that you have got is the energy of the system whose wave function is psi. And if the operator you have applied is momentum operator, like P operator is applied on wave function, and something constant time wave function has appeared, then it means that this constant quantity is the momentum of the system whose wave function is this, whose ket is this. Okay, and similarly, if the operator that you have applied is the position operator, and if this situation satisfies that the wave function, the same wave function comes back with as a multiple of some constant, then that constant quantity will give us the position of the system whose wave function is psi. Okay, so that is what the eigenvalue equation tells us about, and we can test whether a wave function is the eigenfunction of momentum operator or Hamiltonian operator or position operator or not. Okay, and we can test it out. We can find out the probabilities, we can find out the uncertainty and other parameters as well. So we'll be doing it later on in the videos. And yes, for now this is it. And I hope you people know that what is Dirac notation. It's simply a notation that is used to represent states and operations in quantum mechanics, and we have seen the operations. Okay, we have seen those operations. They normally are the scalar products and the incorporation of operators in them, incorporation of some squares, additions, subtractions in them, and we should know what they actually mean, what a term in bra means and what a term in ket means, where we have to take the transpose and conjugate and all that stuff. So I was telling you about one thing, that if the vector that you have is in matrix form, then if you want to find out its corresponding bra vector, then you have to take transpose of that matrix plus the conjugate. Okay, so it only happens with matrices. Okay, it doesn't happen with other forms. For example, as I told you people earlier, if some function is given, let's say if psi is equals to e to the power iota kx, then it's a ket. And if you want to find out its bra, then it's simply to take its complex conjugate, and we'll have to do this thing. We'll replace iota by minus iota. But if it's in this form, if this is the ket, then if you want to find out its bra, then what you have to do is to take the transpose of it and then conjugate of it. If it's in matrix form, then what happens is we will take the transpose first. So the row changes, the column changes into row. So we have 0 e to the pi iota kx, and then we have to take the complex conjugate as well. So complex conjugate means replacing iota by minus iota. So e to the power minus iota kx, that is its bra vector. That is the ket vector, and here is its bra vector. All right, so if you talk about the matrices, then a ket represents a column matrix. It's a column vector, and a bra is the row vector. Okay, that's another wording that we use for the kets and bras. So ket is a column vector and bra is a row vector in Hilbert space. So yeah, that is it for this video. I hope you got it. And here I have written them in neat form, so you can see this is the wave function. It's a ket vector, it's a column vector, bra vector is like that, it's a row vector, and we take the complex conjugate of ket, and then we have bra-ket vector. Bra-ket vector means the scalar product of bra and ket. Okay, bra-ket vector means they are coming together, first bra and then ket. It's a scalar product of psi and phi. And norm is real and positive. Norm means self product. So self product is positive and real, and if they are normalized, then that is equals to 1. Okay, norm, which is psi with psi product, this is never complex. Okay, so by positive real mean it is never negative, and it's always real. It always lies in real space. It is never a complex quantity. Then we have orthogonality condition like that. Phi and psi should be equals to 0. That's the orthogonality condition. Some wave functions satisfies it and some doesn't. Those wave functions which satisfy the orthogonality condition are said to be orthogonal, and those that doesn't are not orthogonal. So then we have this eigenvalue equation. Operator applies on psi, and we have a into psi. So a is the eigenvalue. If it's constant, if a is a constant quantity, it's a constant quantity, then a is the eigenvalue of a, and psi is the eigenfunction. If a is constant, okay, I'm stressing it again and again. We'll see it later in the videos where we'll be testing some of the wave functions, being the whether they are the eigenfunctions of, let's say, momentum operator or not. So we'll be testing out all of these things, and we'll understand them later in the video. But let me tell you that what does that mean. And sometimes if we want to write function as a function of r and t, we have this situation, right? And if you only want to write it in the form of, this is not a common way, okay, we don't frequently use it, but you should know that if that thing appears, then what does that mean? So it means that we have that ket vector, and it is a function of r and t, so you can write r and t here. It's just an additional thing. So yeah, and we have this expectation value expression. We'll see these formulas in later video, where I'll be mentioning all of the important formulas that involves the expectation value, probability calculation, uncertainty calculation, and yeah, that's it for this video. And like, share, and subscribe, and let me know if you are confused about any of these things. Okay, so goodbye.